Hey everyone, and welcome. So, have you ever heard the term data structures and immediately thought it sounded, well, super complicated? Something just for coding geniuses? If so, this is for you. We're about to break it all down and show you that it's actually a really simple, incredibly powerful, and absolutely essential idea. So here's our game plan. First, we'll get right to the core idea, the smartest way to store things. Then, we'll figure out why computers care so much about this. After that, I'll give you a simple map of all the different types. We'll cover a few key rules, and then the best part, we'll see how this all connects to the real world. Sound good? Let's go. Okay, let's dive right into this. At its heart, a data structure is really just about one thing, being smart about how you organize stuff. And this, right here, is the perfect way to think about it. Imagine all your books are just chucked into a giant pile on the floor. I mean, you still have all the books, all that data is there, but trying to find a specific one, it'd be a total nightmare, right? Now picture those exact same books, but they're all neatly arranged on a bookshelf, maybe sorted by author. See? It's the same information, but the structure makes it 1,000 times easier to use. That right there is the whole idea. So here's the key takeaway. A data structure isn't the data itself. It's the container. It's the bookshelf. It's the system we use to organize our information so we can get to it and work with it, easily and fast. Let's just make that distinction crystal clear. When we say data, we're talking about the raw stuff, the individual pieces, like the number 10 or the name Ollie. But a data structure, that's how we organize those pieces, like putting a bunch of numbers together in an array. One is the book, the other is the bookshelf. Simple as that. Okay, so why do we care so much about this? And maybe more importantly, why do computers care? Well, it all comes down to one word: performance. This isn't just some abstract theory. It has huge consequences in the real world. If you could ask a computer what it's constantly worried about, it would give you just two answers: speed and memory. How fast can I do this, and how much space is it going to take up? These two things aren't infinite, and basically, every program ever written is a battle to use them as wisely as possible. And this is where our hero, the data structure, swoops in to save the day. Choosing the right one is the key to solving the computer's biggest worries. It lets us store things using less memory, find what we need in a flash, and change things around without everything breaking. And believe me, the stakes are incredibly high. Choosing the wrong structure, or even worse, no structure at all, is just a recipe for disaster. It's literally the difference between an app that feels quick and snappy and one that just crawls to a halt and crashes the second a few people try to use it. All right, now that we know why they're so critical, let's get a bird's eye view, a sort of map of the data structure world. Don't worry about memorizing every little detail here, just focus on the two big families. Pretty much everything boils down to these two categories. On one side, you've got linear structures. This is where data is laid out in a sequence, just one thing after another, like a simple to-do list. And on the other side, you've got nonlinear structures, where data is connected in more complex ways. Think of a family tree or a big web of city streets. So for linear structures, you've got some common examples you've probably heard of, like an array, a linked list, a stack, and a queue. They all follow that simple, one after the other rule. And for the nonlinear side of things, the big ones to know are the tree, which is all about those parent-child relationships, and the graph, which is perfect for modeling complex networks where anything can connect to anything else. So, we've got our map. Now let's learn a couple of the essential rules of the game, the core principles that guide how we design and use these structures in the real world. Now, this is a really important idea. It's called the abstract data type, or ADT. The best way to think of it is like a contract. The ADT tells you what you can do, like you can push something onto a stack or pop it off, but it totally hides how the computer actually does that on the inside. So as the programmer using it, you don't have to worry about the messy internal details. You just get to use the simple, powerful commands. So how do we actually compare which data structure is better for a job? Well, we use something called time and space complexity. Now, please don't let that name scare you. The key idea here is not about timing things with a stopwatch. It's about understanding how the need for time or memory grows as we add more and more data. It's a way to predict if our app will stay fast or fall apart. All right, we've covered the what, the why, and the rules of the game. Now for my favorite parts. Let's connect all this theory to the real world that you use every single day. This is where it all just clicks. An array, that's just like the seats in a movie theater. Each one has a specific number. A linked list is like the cars of a train, each one hooked up to the next. A stack? Come on, that's just a stack of plates you always take from the top. A queue is what you do every day. It's a line at a ticket counter, first come, first served. A tree is like a company's org chart, and a graph is just a city roadmap. See? You've been using these ideas your whole life without even realizing it. Now, in modern programming, the philosophy isn't just about building these things. It's about using them safely and smartly. The goal is always to lean on powerful, pre-built tools to write code that's reliable and correct, rather than trying to be clever and accidentally creating bugs. So you might be thinking, wait, do I have to build a whole train from scratch every time I need one? And the answer is, thankfully, no. You learn how to build these things from the ground up so you deeply understand how they work, which is super important for job interviews and designing big systems. But in your day-to-day coding, you'll almost always use the powerful, super optimized versions that come built right into your programming language. So I want to leave you with this final thought. Go ahead and open your favorite app, Spotify, Instagram, whatever it is. Based on what we just talked about, what data structures do you think are humming away behind the scenes to manage your friends list, your playlist, or your game world? Once you start looking for them, you'll start to see them absolutely everywhere.